Welcome. In this session on natural deduction, we'll explore ways that we can remove an existential quantifier from a proof. Let's start by recalling from propositional logic. Let's recall the rule of disjunction elimination. And disjunction elimination said that if at least one formula is true, and we separately assume that these formulas are true, then a goal assertion is true. And the way that we wrote that was, if we had a disjunction of two formulas, and if we opened an assumption box with the left disjunct as the assumption, and we could go and conclude a third formula, and if we could open up a disjunction box with the right disjunct, and we could conclude that same formula, then by using the rule of disjunction elimination, we could conclude that new formula. And this strategy was something that we used mainly in forward reasoning. Now, let's consider existential elimination. We can think of this as an infinite form of that disjunction. That is, we can say, when there exists an x such that formula phi, what that means is there's an infinite possibility of those x's, and at least one of them applies in that formula. So what we're saying, if some one or more are true, and we can assume one of them, then if we can deduce that additional formula, then it must be true. So here we'll have the usual side condition, which is, what we'll do is, when I say we'll assume a fresh variable, right? So side condition, it'll be our fresh variable once again. And by that, I mean is there will be a term, and this term is almost always a variable for us, but a term t that is free for whatever the existential quantifier is using in the formula. The way that this is written is, suppose that we have an existentially quantified formula. And now what we'll do is we'll assume two things. Let's introduce a fresh variable or term, and now we'll take that quantified formula and we'll substitute that term for whatever this variable is. And if we can then conclude a new formula, we'll say that that new formula can be written in our proof, and this is existential elimination. Let's try a simple example. So let's suppose that our statement is, some poodle is quiet, therefore something is a poodle. And we'll write that as, there exists an x such that x has property p and x has property q. We can conclude that something has the property p. So to do this proof, as usual, we'll write down our premise, which is there exists an x that has both property p and property q. So that'll be a premise. And our conclusion will be, there exists an x such that x has property p. If we look at this and look at this, it's not clear which way we should go. So what we'll do is we'll try our forward reasoning using our new rule of deduction. And that would be, we would introduce a fresh variable. So I'll introduce the fresh variable z. So I'll take z, and then the rule says I now take the formula that is being quantified and I substitute this fresh variable into that formula. So I will then, on the same line, put p of z and q of z. I'll write that as an assumption. And I have to have a box here. And then the rule says that I should put the reason for this goal line down now. So I'll say that that's an existential elimination. And it will be based on line 1 for sure, and then it will be based on the reasoning from the box that starts at 2, and I don't know how far it goes yet. And then the last thing I do is I take the goal formula and I copy that into the box. So I copy in here, there exists an x that has property p. I now review my assumption and everything preceding it that's within scope. In this case, I look at my assumption. What was previously in scope isn't very helpful, but the assumption itself is helpful because my goal is to prove that something has property p, and now I know that that whatever value that variable takes on, it's got that property p and it's also got property q. That means that I can now go back to propositional logic and I can conclude that that fresh variable has property p, and so that would be line 3, and that is justified by conjunction elimination type 1 based on line 2. And now, if something has property p, then there exists an x that has property p. So that I can justify by using existential introduction based on line 3. And now I've completed my box. Everything is finished. And so I simply assign this as line 5, and my reasoning is in the box lines 2 to 4. And so that proof is complete. Let's try a slightly more complicated one, and what we'll do is we'll use this rule and we'll use another predicate rule, and we'll use some reasoning from propositional logic. So let's say that what we want to show is something is even, so not everything is odd. And I could make that sequent. I could say there exists an x that is not odd, therefore it's false that everything is odd. And to do this proof, I would start by putting down my premise. So there exists an x, not p of x, so that is a premise. Let's block this off to be sure we don't run too far over. And I would write my conclusion, which is for all x, it's false that for all x, x has property p. I now take a look at my premise, take a look at my conclusion, and say, do I want to reason forward or backward? Well, I certainly could start reasoning forward, and I could just apply this rule, and then I would have not p of x, and then it's not clear at all to me how I would go about proving this. So instead, let's reason backwards. So this has, if we parse this, the parse tree shows us that this is a negation of a more complicated formula, and I could use negation introduction. So I could use, this is a proof using contradiction. So to do that, what I would do is I would create my assumption box. And I would write the reason for the assumption box now, so that would be negation introduction. I write the top line, which is the unnegated formula, so I would write for all x, p of x, and that's line 2, and that's an assumption. And I would then, because this is a proof using contradiction, I would put the bottom symbol, or contradiction, here. And now I would stand back and say, what can I do? Well, let's see. I'm trying to arrive at a contradiction, and I have two quantified formulae. Let's take a look, because this is technically really important, is if I were to use universal elimination, I would have a fresh variable. The trouble is, when I then use existential elimination, I would have a fresh variable. That can't be the same variable as this. Really important is the order in which I apply these rules matters enormously. So can I write existential elimination inside this box? And the answer is yes. And the reason is that this is within scope. Now, it's a little bit unfortunate that we picked x here, but that's actually, sometimes a bit of confusion is good for us because it really makes us think. So I could apply existential elimination inside this box. And if I do that, then I'm opening up a new assumption box. And when I open that up, I'll pick variable w. So I fill in the top line, which is my fresh variable. W does not appear anywhere else. And I then substitute w into the formula that is existentially quantified. So I then put not p of w, and that is an assumption. I then take the gold symbol and copy it into the box, so it's offset a little the way that I've drawn it. And I now can assign this a number, and I can then ask myself, using this assumption and everything that precedes it that's within scope, what can I do? Well, here I see not pw, and here I see everything is p of x. Well, am I allowed to use universal elimination and conclude p of w? And the answer is certainly I can, because if everything has the property, then w has the property. So I can write p of w as the fourth line of my proof, and I can then say that that came from universal elimination based on line 2. Oh, when I wrote this, I forgot this. Usually what I do is when I write the assumption box, I put the reason for the assumption box immediately so that it's clear to me that I don't need further deduction there. So this was based on existential elimination using line 1 and then using the box that begins at 3. So now, let's return to our proof. So now I have p of w, not p of w. That is a contradiction. So I can use negation elimination based on line 4 and line 3, and that completes this box. And so if this box is complete, I can assign that a line number, and I can then say that this is justified. Existential elimination, the quantifier was on line 1, the box is 3 through, now that is 5. I can assign that the number 6. And now this outer box is complete. I can say that this was justified by negation introduction, the box that started on line 2 and that ended on line 6. And we've completed our first proof that uses 2 rules for predicate logic and a proof involving contradiction.